German Q&T has officially launched the NPU-2, the world's first commercially deployable photonic processor designed for AI and high-performance computing. And the announcement marks a turning point in computing history. For years, the idea of performing computation with light instead of electrons has been treated as a futuristic dream, promising in theory, difficult in practice, and always 10 years away. But with this launch, the gap between research and reality has collapsed. The NPU-2 is a 19-inch rack-mount server running Linux, using PCIe, shipping to customers in the first half of 2026, and delivering performance numbers that are so far beyond conventional GPUs that the industry is finally being forced to confront a new era. And it arrives with claims that are almost uncomfortable for the silicon world to hear. Up to 30 times lower energy consumption and up to 50 times higher performance on real AI and scientific workloads compared to traditional CMOS architectures, including the most advanced GPUs from Nvidia. But what makes the launch even more shocking is the speed at which this technology is evolving. A chart in Q&T's own documentation shows that in just 2 years, their photonic processor generations from NPS Gen 0 to Gen 2 have advanced at a pace equivalent to the semiconductor industry's entire progression from the Intel 4004 in 1971 through the Pentium era of the 1990s, then through Nvidia's classic GPU age with the GTX 480 in 2010, all the way to the A100 accelerator in 2020. Silicon needed 50 years to move from the Intel 4004 to Nvidia's A100. Q&T's photonic platform compressed that same journey into less than 24 months, and the numbers hidden behind that timeline are even more unbelievable. Q&T went from roughly 0.01 MOPS in Gen 0 to a staggering 1 billion MOPS in Gen 3, a 100 million-fold performance leap. No computing hardware platform in history has ever shown that kind of generational jump. One detail that cannot be overstated is that Q&T became the first company in the world to achieve true 16-bit floating point precision inside a photonic circuit. Until now, optical processors could barely reach a few bits of noisy analog accuracy. Hitting FP16 is the reason photonics can finally train modern neural networks. Without this breakthrough, photonic computing would still be a scientific curiosity. With it, it becomes a genuine successor to GPU computing. And this isn't a small incremental improvement. It's not a 10% speed boost or a new memory layout. It's a completely different physics model. GPUs compute by flipping billions of microscopic transistors, billions of times per second. Every single arithmetic operation, addition, multiplication, activation functions, must be broken down into digital instructions, cached, executed, and synchronized across compute cores that generate massive amounts of heat. In the NPU-2, these operations are not simulated digitally at all. They are embedded into the way light behaves, summation, multiplication, Fourier transforms, and even non-linear functions aren't computed. They simply happen as photons pass through engineered structures inside thin-film lithium niobate. This is where photonics shatters one of the oldest rules of digital computing. In CPUs and GPUs, non-linear layers are always the slowest part of every network. They are the bottleneck. They are the operations that force hardware designers to invent new architectures and caching systems. Yet, on Q&T's photonic hardware, the non-linear operations, at the very part of the network that slows GPUs down, become the fastest part of computation. The benchmark even shows that non-linear networks on a CPU collapse to around 2% of linear layer performance. On the NPU, non-linear layers don't just avoid that collapse, they actually run faster than linear layers by a factor of 1.5. This reversal is so fundamental that it essentially rewrites how neural networks should be designed. Models that are mathematically elegant, but impossible to run efficiently on GPUs, suddenly become practical on photonic hardware. That single sentence captures why this launch is so disruptive. In a GPU, a simple 8-bit multiplication requires around 1,200 transistors working in perfect synchrony. In Q-Ant's photonic processor, the same multiplication is performed by one optical element. A Fourier transform, one of the heaviest operations in modern AI and physics models, requires millions of transistor cycles on a GPU, but on the NPU2, it is performed by a single waveguide path. The math is not represented as code, it is carved into the material. This allows the NPU2 to sidestep the fundamental constraints that GPUs are colliding with. GPUs burn enormous power because electrons must be pushed through resistive paths. Photons do not behave like that. Once light is inserted into a waveguide, it travels with minimal loss and almost no heat generation. A photonic matrix multiply can consume a fraction of the energy required by an electronic one. And because the operations are analog and continuous, not digital and discrete, the NPU2 can represent complex mathematical relationships without exploding the number of necessary parameters. Q-Ant demonstrated this with real tests, not theoretical claims. When they trained a non-linear photonic neural network for image classification, the system reached the same accuracy as a CPU-based model, with far fewer parameters and far fewer operations. When they applied the architecture to Kolmogorov-Arnold networks, mathematically powerful models used for operator learning and function approximation, they achieved accurate results while reducing the parameter count by 40% and the total operations by nearly half. For image recognition on CFAR-10, the photonic network was able to classify images using only around 100,000 parameters and 200,000 operations. The conventional digital approach needed roughly 300,000 parameters and over 1 million operations, and still performed worse. This is where the 50 times faster claim becomes real. It isn't that a single photonic operation is 50 times faster than a digital one. It's that the entire architecture of the model changes to take advantage of the analog nature of light. A smaller network, doing the same or better work, is the deepest form of efficiency improvement. It means training becomes cheaper, inference becomes instant, and hardware requirements shrink dramatically. To understand why this is a turning point, you need to look at what GPUs are facing right now. Nvidia's latest generation of data center GPUs are approaching 1,000 watts of power consumption per card. Cooling these machines requires complex liquid systems, and the cost of running a modern AI cluster is dominated not by the compute hardware, but by the electricity and water required to keep it alive. Data centers around the world are hitting energy caps, forcing companies to delay expansion or negotiate for additional grid capacity. And transistor scaling is approaching the limit, where shrinking devices introduces more quantum leakage and more heat than gains. At 3 nanometers, we are nearly at the edge. The next steps, 2 nanometers and below, require fabrication facilities that cost between $50 billion and $60 billion. Q-Ant's photonic approach bypasses this bottleneck completely. Their processors do not rely on bleeding-edge silicon nodes. They fabricate their optical circuits using thin-film lithium niobate, a material with exceptional electro-optic properties, inside refurbished semiconductor lines originally built in the 1990s. That is one of the strangest ironies in modern computing. The next era of AI acceleration may not require the world's most advanced fabs at all. You can manufacture photonic NPUs in facilities older than Google, Apple's iPhone, or even the first Nvidia GPU. Building these chips was not easy. The entire photonics industry has been struggling with stability, noise, and precision for years, especially when trying to produce reliable analog optical circuits. Q-Ant solved these problems by integrating the entire optical stack into a single monolithic material, eliminating the challenges that come from mixing silicon, indium phosphide, or other photonic materials. This uniformity allowed them to achieve the precision that modern AI requires and build circuits stable enough to deploy in real-world servers. The NPU-2 improves on the first-generation system that QANT deployed in European research centres. The new version features enhanced non-linear processing zones, lower noise analog units, and a redesigned architecture optimized for real neural network models. All of this comes wrapped inside a traditional server. The T native processing server is a standard 19-inch rack mount system running Linux on an x86 host CPU with multiple NPU cards connected through PCI Express. Developers interact with the machine using familiar languages like C++, Python, and QANT's algorithm library called QPAL. You import libraries, write models, and let the compiler determine which operations should be executed in light and which should remain digital. This hybrid approach is crucial because photonic computing does have one unavoidable limitation: photons cannot store information. Light does not sit still. Whenever the model needs memory, state retention, or intermediate activation storage, the system hands the data back to digital memory. QANT's architecture embraces this limitation. Instead of fighting the physical constraints, they allow light to handle the transformations it excels at: matrix multiplies, non-linear functions, operator networks, while traditional memory systems handle everything else. The result is a processor that is not trying to replace GPUs, but is trying to offload the parts of AI computation that are becoming unsustainably expensive to perform digitally. In manufacturing and logistics environments, the NPU-2 can power computer vision systems that identify defects, track moving objects, and perform real-time analysis without requiring racks of GPUs. In physics-based simulation, the photonic processor accelerates partial differential equations and operator networks, enabling new forms of materials modeling and fluid dynamics. In robotics, it powers faster control loops with lower energy footprints. And in the future, photonics may become the backbone of hybrid AI models that merge statistical learning with physical modeling, a direction many researchers believe is necessary for the next stage of AI development. What makes this moment historic is not just the technology, it's the timing. The world is on the edge of an AI energy crisis. Every new model demands more GPUs, more power, more cooling, and more money. Cloud providers are already negotiating with governments for grid expansion. Companies are delaying deployments because the electricity simply isn't available, and the pace of AI progress is now directly tied to the physical ability to power and cool trillions of digital operations. The NPU-2 represents a radically different path forward. Instead of adding more silicon, it changes the substrate of computation itself. Instead of fighting heat, it avoids generating it. Instead of requiring $50 billion fabs, it opens the door to decentralized manufacturing. But the real question remains: if a photonic processor can deliver a 100 million-fold performance leap in 2 years, what happens when this technology reaches its 5th generation? Comment your thoughts below. And if you want the real story behind the world's fastest moving AI and tech breakthroughs before the headlines, make sure to like and subscribe to Evolving AI for daily coverage.